All right, I think we'll go ahead and get started. Welcome everybody to our distinguished lecture series. My name is Jeff McDonald, and on behalf of the Global Institute for Water Security and the Global Water Futures Project, I would like to welcome you and thank you for joining us. Don't forget that next week we have Megan Kohner. Megan is at the University of Illinois in Champaign-Urbana, and she'll be talking about the food, water, energy nexus. And before we get started today, we just wanted to remind you, as we do each week, that we are coming to you virtually and live and recorded for those that are watching afterwards from Treaty 6 territory, homeland of the homeland of the Métis. And we pay our respects to these First Nations and Métis ancestors of this place. And through our work in water security, we hope to reaffirm our relationship with one another. Today, it's a real pleasure to welcome Professor Junguo Liu from Southern University of Science and Technology, otherwise known as SUSTech. SUSTech has just exploded onto the scene in the last 20 years or so, maybe less, with incredible grouping of professors and researchers. And Junguo is a premier example of that. He's a chaired professor in the School of Environmental Science and Engineering. He did his PhD at ETH Zurich, completed in 2007, and has really gone on to become an international thought leader in the area of water resources and management and the coupled human water system. For this, he was selected as lead author of the IPCC 6th assessment report, and he's received over 30 awards. It's quite remarkable. One last year that I'm very aware of through the American Geophysical Union. This is the Witherspoon Award. This is the mid-career award in hydrology, and by far our most competitive award. And it's just a thrill to have Junguo be the recipient of that last year and to give the Witherspoon lecture. He also received Outstanding Young Scientist Award from the National Science Foundation of China and the Outstanding Young Scientist Award from the EGU in Europe, the European Geosciences Union. And again, that is only 10% of the awards that I could list here. But beyond his incredible research and recognition, he's really been a tireless contributor to the community, working with several journals, but also the service contributions through the IAHS, the International Association of Hydrological Sciences, where he leads the working group on water scarcity assessment in the Pantarei program. So I'm just so thankful that you can join us today, Junguo, and looking forward to your seminar. I know the time difference to where you are in Shenzhen is difficult, but again, we're so appreciative that you are here, and I'll turn it over to you now. Thank you.
Okay, thank you. So good morning, good afternoon, good evening, ladies and gentlemen. Thanks, Jeff, for inviting me to give this talk for the distinguished lecture series at the Global Institute for Water Security and Global Water Futures. Specifically, I would like to thank Jeff McDonald. Jeff is a well-recognized hydrologist and a great collaborator of mine. He has given me a huge amount of support for my research and career in the past few years. Jeff is also very active in helping junior hydrologists and young scientists from China and all over the world. So my name is Junguo Liu. I'm a vice president of the North China University of Water Resources and Electric Power in China. So this is my new affiliation. And I'm also a chair professor at the Fountain University of Science and Technology, as introduced by Jeff McDonald. And very recently, we established a lab called the Henan Provincial Key Lab of Hydrosphere and Watershed Water Security. And this lab has many common research topics with the Global Institute for Water Security. So today, I would like to first introduce the two organizations I'm working on. The first one is the North China University of Water Resources and Electric Power. And this is co-sponsored by the Henan province and the Ministry of Water Resources of China. It is a teaching and a research university established 71 years ago. And it is currently the only Chinese university with water resources in its name. So it is a very important university for water resources education and also for research. And the current Chinese Minister of Water Resources was educated from our university, and the previous two ministers of water resources were also educated in our university. And we also had several alumni, including one very important writer called Junguo Liu. He wrote a very famous novel called The Three-Body Problem. That is one very interesting novel, the science fiction book, and I like that book very much also. So this is the place where the university is located. It's called Zhengzhou. And we also see that Zhengzhou is the capital city of the Yellow River Basin. So it is a very important city for the Yellow River Basin. And another organization I'm working is the Fountain University of Science and Technology. This is a very young university established in 2010 in Shenzhen. Shenzhen is called the China's Silicon Valley. And SUSTED has become a very important research university. And it was ranked as the top university in the world. And based on the ranking of the Times Higher Education, it was ranked as the top 8 university within the mainland China. So I would like to talk about water scarcity today. And first of all, I would like to give you some background information. As introduced by Jeff McDonald, I was involved in the IPCC assessment report. And I'm specifically working on chapter 4, water. And for this chapter, the first key finding is that the intensification of hydrological cycle due to human-induced climate change is affecting water security. So the water security issue is very important. And water scarcity is one aspect of the water security problem. And currently, 4 billion people are living in regions with water scarcity. So according to the World Economic Forum's Global Risk Report, water crises are classified as the largest societal risk. So among all the water crises, water scarcity is a very big concern of SDGs. For the target 6.4 of the SDGs, the Sustainable Development Goals, there is one specific target to address water scarcity and substantially reduce the number of people suffering from water scarcity. So today I would like to talk about 4 Ws. The first is what is 3D water scarcity? Second, how did 3D water scarcity assessment involve? The third is what approaches are used to assess the 3D water scarcity? And the last part is where was 3D water scarcity applied? So I would like to talk about the definition of the 3D water scarcity. So water scarcity is the lack of fresh water resources to meet the standard water demand of required quantity or quality. And this demand is either from the social economic sector for human being or from the ecosystems for the nature. And here, the 3D water scarcity has 3 dimensions. The first is the quantity dimension, the second quality dimension, and the third one is the ecological dimension. So for the quality-induced water scarcity, it is defined as the in the situation when the quantity of water is not sufficient to meet human demand. And the quality-induced water scarcity is defined as the situation when quality of water is not sufficient to meet human demand. And the ecological water scarcity is defined as the situation when quantity or quality of water is not sufficient to meet demand of ecosystems. So here for the first 2 dimensions, they focus on human beings, and the third one focuses on ecosystems. So I would like to briefly show you the history of water scarcity assessment. And the water scarcity assessment started from the 1970s, 1980s. And Martin Falkenmark was the first person to quantitatively assess water scarcity. And she used an indicator by using the ratio of by using the indicator of water availability per capita. So he developed specifically method to quantify water scarcity, and this indicator is later called the Falkenmark indicator. So we can see that the indicator is based on the per capita water resources. So if we have more than 1,700 cubic meter per capita per year of water resources, then we do not have water stress. But below this threshold, we have different levels of water scarcity. So this indicator, the Falkenmark indicator, is still widely used to assess the water scarcity problems. Another often used indicator is called the criticality ratio. It is the ratio of the annual water withdrawals to water resources availability. So if we have a high ratio, then we may have a serious water scarcity problem. And when this ratio is higher than 40%, we have high water stress problem. So this criticality ratio was often used to assess water scarcity. These are 2 very important papers published in Science in the early 2000s. And we can see the spatial distribution of water scarcity. Like here in this map, the regions in red means the regions with water scarcity. And also this paper was also published by 2 Japanese scientists. And also we can see the regions with water scarcity with the red color. So water scarcity was assessed with the criticality ratio with high spatial resolution starting from the early 2000s. And if you look at the literature, you can find more than 100 indicators for water scarcity. And also we can see that the number of publications increased with time. So there are also many methods or many indicators to assess water scarcity. So in this table, we show the most important methods or the most important indicators for water scarcity assessment. So there are 9 indicators in total. The last one, the TQE indicator, is from our team. And for the remaining 8 indicators or the 8 methods, mainly they are used to assess the quality-induced water scarcity, but very few were used for the quality-induced water scarcity, and similarly, very few were used to assess the water scarcity for ecosystems. So we can see that the science community mainly focus on the quantity-induced water scarcity assessment. However, the facts are more than 80% of the wastewater resulting from human activities is discharged into rivers and sea without any pollution removal. And roughly 80% of the marine and coastal pollution originates on land. So the water quality problem is very serious for all over the world. And for SDG, there are specific targets to improve water quality and also to prevent and reduce marine pollution of all kinds. So we have to address the water quality problem, and also the ecological degradation is another very serious problem for our Earth. So to conclude, since the 1980s, water scarcity assessment has mainly focused on quantity-induced water scarcity. However, with intense human activities, quality-induced water scarcity and ecological water scarcity have become very important constraints for sustainable development. There is a need of 3-dimensional water scarcity assessment by considering not only the water quantity, but also the water quality and also the ecological water scarcity. So the second part of my talk about the involvement of water scarcity assessment. So for my team, we started to consider the quality-induced water scarcity after I came back from Switzerland. The first project I worked on is to restore the mother river of Beijing, or the Yongding River. So when we visited many rivers in Beijing, we can find that there is very limited water in the river, and also pollution is another very serious problem. So when we consider the water scarcity assessment for many rivers in Beijing, and certainly it's easy to quantify the quality-induced water scarcity because we have many indicators for such a purpose. But at that time, it's difficult to quantify the quality-induced water scarcity. So we try to find an approach for such an assessment. And then we integrate the concept of green water footprint. The green water footprint concept was introduced by Ian Hochstra. He was a scientist from the Netherlands. He defined the green water footprint as the total amount of fresh water needed to assimilate pollutants to meet specific water quality standards. So if the green water footprint is much higher than the fresh water availability, then we may have quality-induced water scarcity problem. So we integrate the criticality ratio method with the green water footprint approach. We develop a method to key and quantity-induced water scarcity, or the so-called two-dimensional water scarcity assessment. So this is assessment for Beijing as a whole. We also developed such a tool called the water scarcity meter. And here in this meter, you see there are two triangle bars. If the blue triangle bar is above the threshold here, we may have quantity-induced water scarcity problem. And if the green bar is above the threshold here, we may have the quality-induced water scarcity problem. And this is a result for Beijing as a whole. And we can conclude that for Beijing city, it has not only the quantity-induced water scarcity problem, but also the quality-induced water scarcity problem. So Beijing city was suffering from both quantity and quality-induced water scarcity. And we also assess the water scarcity situation for different river basins within Beijing. And we found that for all the river basins in Beijing, they all had quantity-induced water scarcity problem. So that means that all the river basins, the people, they do not have sufficient water resources. So the quantity-induced water scarcity problem. But not all the river basins had quality-induced water scarcity problem. Only two river basins, they had the quality-induced water scarcity problem. So with such approach, we can also assess the two-dimensional water scarcity for all the provinces in China. So this is the result for the assessment. And in this map, the provinces in red means the regions with both quantity and quality-induced water scarcity problems. So we can find that many provinces in the northern part of China, they suffer from both the quantity and quality-induced water scarcity. And the provinces in green shows the quality-induced water scarcity. So for those provinces, they only had the quality-induced water scarcity problem. And for the provinces in blue, they do not have water scarcity problem. So from the results, we can also conclude that quality-induced water scarcity is more serious than the quantity-induced water scarcity, because you see the provinces in red and in green, these provinces, they had the quality-induced water problem, but only, so that means for all the provinces with quality-induced water scarcity problem, they always had the for all the provinces with the quantity-induced water scarcity problem, they always had the quality-induced water scarcity problem. So quality-induced water scarcity is more serious in China. So for this approach, it was learned by many other scholars all over the world. And this is another study, another paper published in Nature Geoscience. And this study was led by a group of people from Java in Austria. And they use very similar approach to assess the quality-induced water scarcity for all over the world. And they use approach to assess water scarcity as the ratio of sectoral water withdrawals of acceptable water quality to the overall water availability. So if you read the paper, you will find the approach is very similar. And there are also other recent studies on quality-induced water scarcity assessment. Like this paper was published in Nature Communications by a group of people from the Chinese Academy of Sciences and also other co-authors. And they quantify the quality-induced water scarcity with a very similar approach. And they assess the water scarcity with high spatial resolution for all over China. So this is the two-dimensional water scarcity assessment by including the quality-induced water scarcity. So for both the quantity or quality-induced water scarcity, they mainly emphasize on human beings. So they are both human-centered assessment. As I mentioned, the ecological degradation is very serious for many places in the world. So we also need to consider the water use for ecosystems. So that's the reason why we also need to consider the third dimension, or the ecological water scarcity. And the first time we started to work on ecological water scarcity was the assessment for the Huangqihai Lake Basin in the northern part of China. And in this study, we assessed the water scarcity by considering environmental flow requirements, water quantity, and also water quality. So in this study, we consider the environmental flow requirement based on different health situation of the river, the lake ecosystems. And then we integrate the environmental flow requirements into the assessment of water scarcity. And very recently, this month, we published another paper specifically on ecological water scarcity. And here, if you have a look at this equation, this is the indicator for the ecological water scarcity. We compare the water demand for ecosystem, this E, this is the water demand for ecosystem, with Q. Q is the water supply for our ecosystem. And then we use this indicator to show the ecological water scarcity. And for the Chinese provinces in red or in pink, that means those provinces, they had ecological water scarcity problem. but the provinces in green, they do not have the ecological water scarcity problem. So we can see the spatial distribution of ecological water scarcity. And the provinces with problems are mainly located in the northern part of China, but also for the Guangdong province, where Shenzhen is located. And certainly we can use the similar approach to quantify water scarcity for all over the world. And we quantify water scarcity with or without considering environmental flow requirement. And we found that the water scarcity can have a very big uncertainty because there are different approaches for the assessment of environmental flow requirement. So that means in order to have a good result of water scarcity assessment, we need accurate estimation of environmental flow requirement. So in the future, we still need to develop good approaches for the assessment of environmental flow requirement in order to get good result for ecological water scarcity assessment. And we integrate the water quantity, water quality, and environmental flow requirement into the three-dimensional water scarcity assessment. And we also published a Chinese article to show how the three-dimensional water scarcity assessment evolved in the past few years. And as introduced by Jeff McDonald, I also worked for the Pantarai program, or the decadal program of International Association of Hydrological Sciences. And we established a working group on water scarcity assessment. And in fact, there is one only aim for this working group, that is to develop methods for water scarcity assessment by considering environmental flow requirements, water quantity, and water quality. So the three-dimensional water scarcity assessment is the only aim of this working group. And we involve a lot of experts from different countries in this working group. And we work together for water scarcity assessment by working together with all these people from different continents and different countries. And this working group was established in the year 2014. And 5 years later, in 2019, UN launched a guideline for incorporating environmental flows in water scarcity indicator. So now I would like to report what kind of approaches we use for the three-dimensional water scarcity assessment. And in our team, we have developed several methods for assessing water scarcity by considering the three dimensions. In order to quantify the quantity-induced water scarcity, we need models to simulate water resources and the amount of water use, or the blue water footprint. And we also integrate economic approaches with hydrological models to assess the water economic systems. And in order to quantify the quality-induced water scarcity, we develop nutrient cycling models and approaches for groundwater footprinting. And in order to quantify the ecological water scarcity, we have developed a model called the Water and Ecosystem Simulator, the WIS model, and also approaches for environmental flow assessment. And in order for better water management and sustainability, we also introduced the stepwise ecological restoration and green infrastructure needs-based solutions for the water management. I would like to briefly introduce these methods. The water and ecosystem simulator. So with such a model, we can quantify different hydrological fluxes and also the storages from the river basin to a global scale. So you can see this is the result for the global assessment. We can quantify different fluxes, storages for different pixels with high spatial resolution. And for this model, we can quantify not only the surface water, groundwater, but also the soil water. The soil water, we call it the green water. And it is now a very important tool for the intersectoral impact model intercomparison project. And in order to quantify the quality-induced water scarcity, we need approaches for nutrient cycling assessment. So we have development approach to assess the nitrogen cycle in the cropland, and we have specific approaches to assess the fixed nitrogen inputs and 5 nitrogen outputs in agriculture. We emphasize on agriculture because the non-point pollution is the largest contributor to quality-induced water scarcity. And this is the result of the assessment. We can quantify nitrogen inputs, nitrogen outputs with high spatial resolution for all over the world. And we found that about 40% of the nitrogen applied in cropland was lost in ecosystems, leading to water pollution, quality-induced water scarcity, and other environmental consequences. Therefore, in order to reduce the quality-induced water scarcity, we need to have a better management of nitrogen and phosphorus also in cropland. And this is a paper published yesterday, and we developed a comprehensive and synthetic database for reconstructing the history of human nitrogen inputs from 1860 to 2019. And for this database, we include the nitrogen inputs on cropland, pasture, and rangeland at a spatial resolution of 5 arcminutes, about 10 kilometers for each pixel. And we have 10 classes of nitrogen inputs. So this is a very big database, and it's already published. If you need the database, you can download from the journal website. We also have developed models to quantify the water use, specifically for the agricultural water use. And the model we developed is called the GAPIC model. So we integrate a field-scale agricultural model with GIS to develop the GIS-based environmental policy integrated climate model to simulate the water use and water footprint with high spatial resolution for all over the world. And we also studied the water use in China for different regions. And we found that the water use in China doubled in the past 4 decades. But the good thing is the increasing rate started to decrease for the water use. So we also developed a very big database for water use for different regions in China. But when we compare the water use statistics with the models, we found that it is still very difficult for current models to accurately simulate water use water footprint with high spatial resolution. So in the future, we still have a very big room to improve our water use models for better simulation in the future, not only for China, but also for other countries. And we also integrate the economic model, the input-output economic model with water use to simulate the water-to-water transfers among different regions and factors. And I would like to show some results. Like this is the pattern of the water-to-water treat embedded in the treat of commodities. And we found that the water-to-water flows went from the western part of China to the eastern part of China, because this part, the provinces are richer than the western part. And the water-to-water transfer account for more than 1/3 of China's water supply. So that means for the water supply in China, more than 1/3 is used to support the community treat within China. And if we compare this water-to-water transfer with the physical water transfer, that is the water diversion project through the water diversion project. So the physical water transfer only account for 4.5% of the national water supply. So water-to-water transfers are much bigger than the physical water transfers. And we also study the role of water transfer, the water and physical water transfer in mitigating water scarcity for different regions. We found like for the rich regions like Beijing, Tianjin, those regions, the water and the physical water transfer can help to mitigate the water scarcity problems here. But because of the water or physical water transfers, and also many provinces, the water scarcity problem may become even worse. Like for Inner Mongolia, if there were no any water or physical water transfers, there were no water scarcity problem. But because this province export a lot of water to other regions, and then the local people need to use a lot of water to support the production of the treated communities, and the water scarcity became a problem for this specific province. So we can see that there are problem transfer among regions through the water or physical water transfers among different provinces. And we also introduce the stepwise ecological restoration because the quality-induced water scarcity can lead to serious water pollution problem for different regions. And the stepwise ecological restoration aims to implement restorative activities by considering different levels of ecosystem degradation. And when the ecosystem is seriously degraded, we need the environmental remediation. But when the ecosystem is moderately degraded, we need ecological rehabilitation. But if the ecosystem is only slightly degraded, then we need the natural restoration. We need to rely on the nature to recover itself without much influence of human beings. So the traditional way to manage water is to rely on many engineering solutions like dams, reservoirs, embankments, dikes, and drainage systems. We call these engineering solutions as green infrastructure. And in recent years, many people, they started to emphasize the green infrastructure to help mitigate the water scarcity problem and to help the water management. And the green infrastructure is a network of natural or semi-natural features that has the same objectives as the green infrastructure. And we found that the green infrastructure is more flexible and cost-effective for providing many benefits. So we conclude that in the future, we need to integrate green infrastructure with the biophysical systems or the green infrastructure to meet the current and future water security needs. And also at the same time, if we think about our educational system, we often have many majors. Like here we have the engineering, and then we may have a major called the hydraulic engineering, and then a direction, a field called the hydrology and water resources engineering, and also a direction of urban hydrology. So for our students, we always learn a small part of the entire engineering field. So in order to address the water sustainability challenges, we think that the knowledge generation needs to move rapidly from a disciplinary linear tree model to an interdisciplinary web model. And we need to solve the water problems. We need to guarantee water security for both human and nature. So in order to achieve this purpose, global challenges are very complex and interconnected. So they can't be addressed by individual disciplines. So success in a web model requires engaging multiple stakeholders right from the start and the institutions that further the interdisciplinarity. So in the last part, I would like to mention some applications for our theory. And as I mentioned earlier, the starting point to consider the quality-induced water scarcity and also the ecological water scarcity assessment, the start was a project for restoring the mother river of Beijing or the Yongding River. And for this river, there are a lot of problems before, particularly this graph shows the amount of discharge for the river, and the water discharge decreased sharply in the past 4 decades. And in the downstream of the riverbed ran dry. The river ran dry. So this is a picture I took when I started to work on the project. And for us as scientists, we need to quantify the water scarcity problem for this river basin. And we also need to set up or establish different objectives, the restoration objectives, specifically to bring sufficient water to meet the requirement of the ecosystem, or we need to increase the environmental flow for these river systems. So this is a picture I took a few years after our project, and specifically in mid-2020, the Yongding River received environmental flows for the entire Beijing section for the first time in this century after almost 30 years of running dry. So I'm very happy to see a much healthier river ecosystem now. And since I worked in Shenzhen for a long time, and I also work on several projects for restoring rivers in Shenzhen. And the problem for the rivers in Shenzhen is the pollution problem. So many rivers, they suffer from quality-induced water scarcity and also ecological water scarcity problem. So in order to increase the quality of river ecosystem, we need to use the stepwise ecological restoration. We need to clean the river. So this is a river we worked on, and you can see after restoration, it become much cleaner than before. And this is the mother river of Shenzhen, that is the Mozu River. And before, it was heavily polluted. You can see the color of the river. It's black because the concentration of pollutants was very high before. But with a project, we work together with the government, the local government, and the entrepreneurs. We work on the restoration project. We bring knowledge of hydrology and also the knowledge of ecological restoration for the river restoration. And the concentration of ammonium for this river decreased sharply from more than 30 microgram per liter to 1.6 milligram per liter now. And the river becomes much cleaner now. You can see the beautiful river. And because the ecosystem, the river ecosystem becomes much better, there were many activities surrounding the river and within the river. And the trekking boat races for Guangdong, Hong Kong, Macau region have been organized for 3 times in the Mozu River after restoration. And thirdly, we have done a lot of research for water scarcity, and we use the research to address the restoration problem for different rivers. And our research has been also highlighted in many media, like in the China Daily, that is China's largest newspaper, and also some other medium like the Henan Television. This is the China Central Television. So they interviewed me about my research, and I talk about water scarcity assessment, and also talk about the ecological restoration for rivers. So to conclude my talk, progress of water scarcity assessment in last 4 decades was largely made on quantity-induced water scarcity, or the one-dimensional model. And in recent years, there has been an evolutionary advancement from a 1D model towards a 3D model that explicitly considers quantity-induced, quality-induced, and ecological water scarcity. And many methods, tools, and approaches are developed to support the three-dimensional water scarcity assessment. And water scarcity research has been applied to solve societally important problems, in particular for river restoration. And I also would like to thank my team for their great support. And also I would like to thank the audience for your attention. Thank you very much for your attention.
Thank you very much. That was really an interesting talk, and we appreciate your time with us, knowing how late it is where you are. Just for the audience, we're not going to have a mentoring session today because of the extreme time difference, but I'm hoping people will have questions. I think they can come in a number of ways. Those that are there live can go to the mic and ask. Those that are watching online can type into the Q&A function, or I think even into chat. And I believe there's even another way where questions can be emailed to Sean and he can pass them to Kim, who's also standing by. So as we wait for hopefully a question or two to come in, I just wanted to ask about the nitrate part. You mentioned that in the water quality assessment. I'm thinking of, for instance, the Loess Plateau, where nitrate-based fertilizers are being applied at a high rate, but it could take 500 to 1,000 years to go through that very deep unsaturated zone to the water table. So there's a lag often with that kind of pollution. I'm just wondering how you account for that, because it seems so very related to what that storage volume might be like, and those recharge and groundwater delays. Any thoughts on that one?
You mean for the nitrogen for the Loess Plateau, right?
Well, as an example of a challenging place to make predictions, I think.
Yeah, it's difficult to make the projections. Yeah. That's correct. For this assessment, mainly we assess the nitrogen balances in history, in the past, and also the next slide for the global assessment. Also, we created a database for nitrogen inputs for the past from 1860 to 2019. But I agree, it's very difficult to project the future nitrogen balances, because we need to consider the amount of nitrogen used in agriculture. Yeah. And we also need to consider the different agricultural patterns, and also need to consider the climate change. So it's much more difficult to think about the future than the past.
Yeah. I think Jay Famighetti's in the audience. I'm curious to know what he thinks about how some of your global patterns map to his GRACE-based assessments of water drawdown. I see a question in the Q&A I can read. This is from Monica. Thank you, encouraging news. Is there any plan to include representation from the African continent in your working group?
That is about the working group for water scarcity assessment. I think certainly it is very important to include representatives from like the Latin America and also Africa, and we are open to all the scientists from all over the world. So if you know any people who are interested in the water scarcity assessment, certainly they can also join the working group. And also, as mentioned by Jeff McDonald, and I'm also working for a few journals, like I'm an editor-in-chief for the physics and the chemistry of the Earth. And very recently, we would like to organize special issues for water scarcity. And we also want to encourage scientists from Africa to be involved in such a special issue and other special issues. So yeah, I agree it is important to include scientists from Africa.
Hey Jeff, I'm here.
Okay, great. Yeah, go ahead.
I feel like I'm on stage here. I'm standing at the microphone. I wish I had my guitar. So thanks, Junguo, for an excellent presentation. So Jeff asked me about, so I don't know if you're familiar with the work that we've done with the NASA GRACE mission and looking at water quantity, right, changes from in water availability over the last 20 years using GRACE. And so the pictures typically look a little bit different. The images look different than some of the stuff you've shown. And I think that's quite typical. So it'd be fun to talk about how we can help integrate those data into your assessments. In part, I don't know if you're doing anything with groundwater, but that could be a big part of it. Recent changes in the high latitudes, we're losing a lot of water up here and across Northern Europe and Northern Eurasia because of all the melting. So be fun to talk about that. Of course, we don't include any quality stuff. So that's, and just sort of getting into the ecological scarcity stuff. So I wanted to point out some work from a student that I co-supervise with Tom Gleason at University of Victoria. Xander Huggins has a paper on that was in, I think, Nature Sustainability earlier this year, which would be a fun one for you to look at and include some different dimensions. And I have a recommendation for you for a person from Africa, and I can email you afterwards. But yeah, just wondering about how much remote sensing data you use and have you looked at any of the GRACE data?
Yeah, thank you. Yeah, if you know any people from Africa, please recommend to me. And certainly, I also think the groundwater is a very important issue. Recently, it became a very important topic, and we need to consider the water scarcity caused by groundwater. I remember there are some papers on groundwater scarcity. I can double check for this.
Sure. Yeah, I can send you some of our work and also some of the work of our colleagues. I think it's really important to start thinking about that. In fact, so I love your use of the 3D water scarcity. I think that's great. But when I saw it, I thought that meant you were talking about surface water and groundwater. So I was a little confused by it. But I think it's awesome. I'm super impressed by everything you presented today.
Thank you. In fact, when we first work on the quality-induced water scarcity, particularly for Beijing, for this assessment, and we specifically discuss the contribution of groundwater for quantity and quality-induced water scarcity. Yeah, for this study, we do some specific analysis.
Thank you.
Thank you for your question.
So I'm aware of the time. We've just gone past the top of the hour. Is there a final burning question? Otherwise, I'll move to wrap up. Tim, at your end, Kim, I might be missing something. I think we'll leave it there. And Junguo, thank you so much for a really clear and interesting talk. So nice to have you with us. Thanks for staying up so late for us today. And look forward to seeing you next time that we can be together, perhaps at AGU. But on behalf of everybody online in the recording, thank you so much for being with us today. Great seeing you.
Thank you, Jeff, for your invitation.